Hello everyone, welcome to the tutorial number 20 of IIT-JAM Chemistry, and this is lecture number 6 of the physical chemistry chapter Gaseous State. We are going to discuss here in this lecture ideal gases and deviations from ideal gas behavior. So how does an ideal gas behave? The kinetic theory of gas is applicable to the ideal gases. So we have learned about the kinetic theory of gas, that it was derived by Maxwell and Boltzmann. And the ideal gases strictly follow different gas laws like Boyle's law, Charles's law, Gay-Lussac's law, Graham's law of diffusion, and Avogadro's law. So let's have an idea about all these laws. Let's start with the Boyle's law. Boyle's law simply says that for a particular amount of gas, that is when n is constant, and if the temperature is kept constant, in that case, the product of pressure and volume is always constant. That means pressure is inversely proportional to volume at constant temperature for a particular gas. Therefore, pressure equals to constant divided by volume, and hence pressure into volume equals to constant. And as a consequence, since pressure into volume equal to constant, then P1 V1 must be equal to P2 V2, and this is equation number 39 as a consequence from the previous lectures. And when pressure is plotted against volume at constant temperature, then isotherms are obtained, and if isotherms of different temperatures are plotted, then the isotherm at higher temperature will be placed over the isotherm at lower temperature. Now next, the Charles's law. Charles's law simply actually it is volume is directly proportional to temperature for a particular amount of gas, and at a fixed pressure for a particular amount of gas, volume is directly proportional to absolute temperature. But this is not the actually Charles's law. Charles's law is actually for each degree Celsius rise in temperature, the volume of a gas increases by V over 273.15 part, where V0 over 273.15 part, where V0 is the volume of the gas at 0 degrees Celsius. And from here, the concept of absolute zero of temperature was obtained. And this way, when 273.15 is added with the degree Celsius, then the Kelvin scale of temperature is obtained. And this way, normal Celsius temperature becomes Kelvin temperature. And that Kelvin temperature is capital letter T, and this is directly proportional to volume for a particular gas at constant pressure. And hence, since V by T equals to constant, then V1 by T1 must be equal to V2 by T2, and this is equation number 40. And isobars would be obtained if volume is plotted against temperature at constant pressure. And here, if at two different pressures the isobars are obtained, then in that case, the higher pressure isobar will be placed below the lower pressure isobar. Next, Gay-Lussac's law. Gay-Lussac's law simply says that pressure is directly proportional to absolute temperature for a particular amount of gas, that is, if n is constant and at a constant volume. Therefore, P by T equals to constant, that is simply P1 by T1 equals to P2 by T2, and this equals number 41. And when P is plotted against T, then isochore is obtained. And if at isochores at different volumes are plotted, then the higher volume isochore would be placed below the lower volume isochore. Next, Avogadro's law. Avogadro's law is actually mathematically it can be said that V is proportional to N. That is, if pressure and temperature are kept constant, then if you increase the number of moles of the gas, then the volume of the gas would also increase. That is, V by N equals to constant. And as a result, V1 by N1 must be equal to V2 by N2. Now, if you take two different gases and they have the same pressure and same temperature, then for the first gas, if it is N1 mole, and the second gas, it is V1 mole, V1 for the first gas, its volume is V1. Then if you take another gas which is N2 mole and it has pressure V2, then when N1 equals to N2, then V1 must be equal to V2, because V1 by N1 must be equal to V2 by N2 for different gases also. So this is the beauty of Avogadro's law. So The Avogadro's law is actually at constant pressure and temperature. If two gases have same number of moles, then they would have same volume. So mathematically we can say that V1 by N1 equals to V2 by N2, and this is equation number 42. Next comes the Graham's law of diffusion, and it says that if R is the rate of diffusion and rho is the density of the gas, then R is inversely proportional to the squared root of density of the gas. And if we take two gases which have equal number of moles and they have molar masses m1 and m2 respectively, having densities ρ1 and ρ2 respectively, at a particular temperature and pressure, in that case, from this Graham's law of diffusion, we can say that the ratio of their rate of diffusion is the ratio of the reciprocals of their square root of their densities, and similarly it is also the reciprocal of the square root of their molar masses also. That means R1 by R2 is equal to root over ρ2 by ρ1, and which in turn is equal to root over m2 by m1, and this is equation number 43. So what about the ideal gas equation? It is simply PV equals to nRT, and if you combine all these laws such as Boyle's law, Church's law, Gaseous law and Avogadro's law, then this P equals to nRT is obtained, and this is equation number 44. And R is the proportionality constant. It is known as the universal gas constant, and it has so many values, but all are same actually. If you change the unit, then the value would change. So it is 1.987 calorie per Kelvin per mole. It is 0.0821 liter atmosphere per Kelvin per mole. It's 8.314 joule per Kelvin per mole, or it is 8.314 into 10 to the power 7 arc per Kelvin per mole. And finally, you can also say it is 0.08314 decimeter cube bar per Kelvin per mole. That is 8.314 into 10 to the minus 2 decimeter cube per bar per Kelvin per mole. Now, real gases. Real gas actually is the gas which are obtained in reality, and ideal gas does not have any existence. But real gases may behave like ideal gas at low pressure and high temperature. So what about real gases? Real gases obey the gas laws only under limited conditions of lower pressure and high temperature. And when they will deviate, they exhibit deviation when temperature drops and pressure rises. Now experimentally, if the pressure volume product is plotted against pressure, then at a particular temperature, say 0 degrees Celsius, that is 273.15 Kelvin, for different real gases such as hydrogen, helium, nitrogen, oxygen, then these types of lines are obtained, and they show ideality. They behave like an ideal gas at very low pressure, preferably pressure tends to 0. In that case, they merge at a same point, that a common point, and from this the value of R can be obtained. The value of this point is 22.711 decimeter cube bar, and if 1 mole of gas, any one of this is 1 mole, so 1 mole of any gas taken, so in place of N we have put here 1, and in place of PV we have put here 22.711, and since the temperature is at 273.15, so this value is also put here, and the result is 8.314 into 10 to the minus 2 decimeter cube bar Kelvin per mole. And if this is converted into joule per Kelvin per mole, then it becomes 8.314 joule per Kelvin per mole. So this way the value of R is determined. And look, the inclinations of these lines, the higher the molar mass of the gas, then inclination becomes more negative. For hydrogen and helium, they have positive slopes, while for nitrogen and oxygen they have negative slopes. So this is the deviation of the real gases from ideal behavior. Now, how does the isotherm of hydrogen gas deviate from ideal behavior? For hydrogen gas, PV is greater than that of ideal gas, and the isotherm thus deviates from that of ideal gas. So this is the isotherm of an ideal gas, while for hydrogen gas the isotherm looks like this. It can be noted from the figure that at low pressure, the isotherm of hydrogen gas and any other real gases has the tendency to coincide with that of the ideal gas. That is, if the pressure here increases along the y-axis, so at the lower value in the y-axis, the pressure is low, and since look, these two lines have the tendency to merge here at low pressure. The molar volume ratio of real to ideal gas, that means molar volume of real gas over molar volume of ideal gas, this ratio is denoted as Z, and Z is known as the compressibility factor. And what about V real, V bar real and V bar ideal? V bar real is the experimentally observed molar volume, and V bar ideal is actually the pressure over RT. So P by RT. Yes, definitely for ideal gas it is PV equals to nRT. For n equals to 1, V becomes V bar. So in that case V bar equal to P by RT, and this is possible for ideal gas. Therefore V bar ideal is equals to P by RT. But this is different from this real gas value. Therefore this value can only be obtained from the experimental results. So this ratio V bar real over V bar ideal is known as the compressibility factor. And if compressibility factor is plotted against pressure, then these types of curves are obtained. This is the gas for the ideal gas, but if real gases are taken, then with increase in molar mass of the gas, there is at the starting point the inclination becomes more negative. So for hydrogen and helium the inclinations are positive, but for nitrogen, methane and carbon dioxide initially there is a negative slope, but after a little bit progression of increasing pressure they also eventually attain a positive slope. And if the compressibility factor Z is greater than 1, say for example for hydrogen and helium, so there is a positive deviation, and for the gases like nitrogen, methane, carbon dioxide, etc., the compressibility factor Z is less than 1. So in that case initially it is Z less than 1, but eventually it becomes Z greater than 1. Okay, so that is why there is a negative slope, but after some time, after some increasing pressure, the negativity vanishes and they also attain some positive character. And if for a particular gas the compressibility factor is plotted against pressure at different temperatures, then these types of curves are obtained. And definitely lower the temperature of the gas, higher is the depth of this well. That is, at high temperature there is a tendency of positive slope, but at low temperature the slope becomes negative. So there is a borderline temperature which is known as the Boyle temperature, where this negativity vanishes and from the starting point at zero inclination the line starts. So that particular temperature is known as the Boyle temperature. So beyond a particular higher temperature known as the Boyle temperature and denoted as TB, there is only positive deviation in the curve, and it is initially having a zero slope. Deviation will be explained on the basis of intermolecular attraction and repulsion forces after the van der Waals corrections. So this van der Waals gas law would be discussed in the next lecture. So that's all about this 6th lecture, and in the 7th lecture we are going to discuss the van der Waals equation. And now let's discuss some questions. The behavior of chlorine is closest to ideal gas behavior at which temperature? So definitely it should behave ideally at high temperature and low pressure. So which one is high temperature and low pressure? Look, this is a real gas, okay, and this is 100 degree, 200 degree, 0 degree, minus 100 degree. So this is the highest temperature, and 10 atmosphere, half atmosphere, half atmosphere, 10 atmosphere. So half atmosphere is lower pressure, so C condition should be optimum. So among the options given above, the highest temperature is 200 degrees Celsius and lowest pressure is 0.50, that is half atmospheric. So option C is the correct answer. And next question, for an ideal gas, the plot that is non-linear is which one? So we have to analyze all these options. Say option A, PV equals to nRT. So PV versus T, isn't it? PV versus T would give a straight line passing through the origin, because this is y equal to mx plus 0 type of curve. Okay, so this should be linear. PV equals to nRT, from which it is PV versus P. So PV versus P. So PV is independent of P. So that is also would be a straight line, but it should be parallel to the x-axis. And P versus B, this is nothing but isotherm. Okay, so this is non-linear, and this is probably the answer. Let's check D. In D, it is said that log ln P, natural log of P, versus natural log of V. So we know PV equals to nRT. So ln P plus ln V becomes ln nRT. Therefore, if T is constant, in that case, this is also linear. Okay, so the correct answer is C. So that's all for today. Thank you and have a nice day.